First session of the year. So this session, we're going to continue some of our discussions about tracing. In particular, there's been a request that we actually look at how traces are captured today, and then how they're tested for whether the preconditions have been satisfied, and then able to be replayed and so forth. So what I want to do is get into first how we capture the preconditions and postconditions of traces, and then test them for replays. Okay, so the first part to look at for tracing, if we look at legion analysis, we're going to look inside the equivalent set operation or equivalent set object, and this is where tracing is going to take place. So effectively, if you're tracing an operation like a task or something like that, the first thing that's going to that task is going to go and do all its physical analysis just like normal, but there's going to be an additional step inside of the analysis, which is it's going to tell the equivalent set, hey, I'm part of a trace and I'm doing recording, as part of capturing the physical trace. And as part of that, we need to update these tracing preconditions, anti-conditions, and postconditions inside of the equivalent set object. And so first, let me show you where that happens, then we'll go take a look at what this trace view set is and talk about what these various different things are. But let's take a look at just where this actually happens. So this is a method that we've looked at before for physical analysis. This is the update set method on the equivalent set, which is effectively the thing that everything that maps a region requirement is going through, on equivalent set to update it, to figure out what copies need to be done to bring data up to date, and then recording, the names of new instances that have valid data, for this particular equivalent set. And most of this code we've looked at before. There's lots of different cases for, reductions and read write and read only and stuff. But all the way down here at the bottom, there's this little part right here at the very end of this function, effectively, which gets run for all the different cases, which says, effectively, if we're doing, some recording of this particular physical analysis, right, we should actually go and update some of the data structures associated with the equivalent set, saying, what are the current valid views? And the idea of this, this update here is effectively the equivalent set is tracking the names of the most recent, preconditions and postconditions for this trace. So a precondition would be like something that the trace is reading for the first time that hasn't been used before, right? And then postconditions are stuff that are effects that the trace actually has as part of its execution, right? So new instances that have been scribbled to or so forth, right? And so what you can see is that in fact, if we don't have any post conditions, we'll make those, and then we'll iterate over all the instances that we actually have brought up to date as part of mapping this particular set of instances for this operation. And we're going to update this tracing valid views. So we're going to call this update tracing valid views function on each one of the instances that we've updated as part of doing the analysis for this operation as it's gone to this equivalent set. So if we go look at update tracing valid views, what you'll see here is that there's a couple of different cases to consider, right? So, let's actually try and work through some of this logic. It's been a while since I've done this myself, but so we'll see if I stumble over anything. But let's see, there's a couple of cases here, right? So the first case is like, if you're reading something, right? If your region requirement, is reading data for the logical region, right? And it's not a discard use case, right, then the first thing you're gonna, let's skip the reduction case and we'll come back to that one in a minute, right? But the first thing we'll do is we'll come down and check to see, whether or not, the current post conditions dominate this, right? And if they do, what that means is that something else has done the write, inside of the trace to this logical region beforehand, and therefore we, this new read that we're doing is part of the trace, but it's not, going to create a new precondition that we haven't seen before. Right, and so we can effectively remove all of the prior writes that have been done to this logical region, inside of the trace, from consideration. But we're going to get out this non-dominated set of expressions and fields, where you see this non-dominated field mask index space expression here. Right, so that's a set of expressions and fields that haven't been priorly written in this trace. Right, and the idea is that this non-dominated set, whatever it is going to be the set of new preconditions that we have to consider as part of this trace. But of course, if it's already been written inside the trace, well, then we're just reading from something else inside the trace, and therefore, it's not considered something we need to record as a new precondition for this trace, right? So we're effectively going to get that out. And of course, if you don't have any tracing post conditions because it hasn't actually been made yet, then everything is non-dominated, right? And so that's an easy case to do. right? And so we come down here. If we don't have one of these tracing preconditions on this data structure, right, you can see these things are pointers because most of the time they're null because we're not actually tracing on equivalent sets. So you have to populate, fill in a data structure here if you don't have one, the first time through. Right, and then what you do is you go through and, for each of the things in the non-dominated set, you record those in the preconditions, right? So this is effectively how we capture new preconditions for the trace, right? The first time you read some logical region inside of a trace that wasn't also written inside that trace, that's a new precondition that the trace has to satisfy if you're ever going to be able to replay it, right? Okay, so effectively that's the reason that occurs, for reading cases. If we look at the reduction case, it's very similar, right? Again, but instead of testing this tracing postconditions, what we do is we trace the anti-conditions, right? Effectively, anti-conditions are, because if you're going to use a reduction inside of a trace for the first time, right? Well, I should say, like, if you're reading and you're reading a reduction view, right? You want to make sure that that it's you want to test to see whether this is a reduction view that is produced inside of the trace or not produced inside of the trace. And if it was produced inside of the trace, it will have one of these tracing anti-conditions because these tracing anti-conditions represent cases where the trace has had to fill the reduction instance as part of the trace execution, and therefore the trace instance can't be a valid copy when you go to replay it, right? And so that we make that an anti-condition. It has to be non-valid in order for it to not be able to be, or in order for it to be filled inside of the trace, right? The reduction instance can't be valid coming into the trace when you go to replay it. And so we test that, effectively here to get the non-dominated set for reading, reduction instances, right? And again, that comes in down here, gets recorded in all the non-dominated sets get recorded in the tracing preconditions. There's a special case here for reductions, right? And I'm trying to remember exactly what this is, right? And effectively what this is, oh yes. So if we've read this reduction instance, right, then we can effectively invalidate it, right? Because effectively it should no longer be considered part of the postconditions for the trace because we've actually ended up reading that particular instance. Right, and of course if we're read only, then we're done. But if we're also writing, if your region requirement is like read write, then you also need to do some additional work. You can see we've got this assert here saying, this is a has, right? And if you're actually writing to this instance, right, this could either be, a normal write, like read write, or it could be a reduction case, right? Then we also have to record this as part of the tracing postconditions, right? And you can see both of these record the new view as part of the tracing postconditions. In some cases, like if you're actually doing like an exclusive write, you might actually invalidate all but yourself, right? Right, because you've actually said this is like if your write dominates some prior set of instances, then you actually need to go through and invalidate all the prior copies or all other instances because your instance is the new only valid copy at the end of this trace, right? And so the way to think of this is this update tracing valid views is tracking sort of a frontier of instances that represent the preconditions and postconditions and anti-conditions for the trace as the trace is being recorded, right? And when you get to the end of the trace, whatever is stored in the equivalent set at the end of that particular trace capture, right, that represents the frontier of preconditions, postconditions, and anti-conditions that the trace will actually record and use for being able to be safely replayed, right? But we kind of do this analysis on the fly as we're doing the recording to actually keep this frontier around inside of each of the equivalent sets that get touched as part of the trace. I've sort of like glossed over some of the details of what these tracing anti-conditions and postconditions and preconditions data structures are. You notice that they're all instances of the same class, this trace views set. Let me actually show you where that is, and let's take a look at that. So that's over here in legion trace.h. So there's a trace view set data structure here. It's got a bunch of methods, but the internal members are actually fairly simple. So it represents a particular index space expression on a particular region tree. It has this owner DID refers to the equivalent set that's producing it. It's sort of a temporary thing. But mainly what it's got is this data structure here, which is a view expers. And this is a type def up here. If we go up here, I think we'll find the view expers type def, I thought. Where did it go? Oh, here it is. I knew it was around here somewhere, right? So a view expers data structure is a map from logical views to sets of index-based expressions with field mass associated with each of those index-based expressions. And the way to think of this is that, it's a set of instances or logical views, right? And the sets of expressions and fields that are associated with each of those views that represent, that either represent them being valid or as a precondition or postcondition, or, as an anti-condition in any one of the data structures over here. And you can see this method actually, or this class actually has a lot of, helpful methods on it. Has things like, you can insert a new view for an expression and a set of masks. You can invalidate a particular view for a subset, right? And of course, these methods will do all the funky, index-based expression math and field mask, intersection tests and subtractions and stuff like that for you. So you don't have to actually deal with those yourself, right? So you can, insert this, and if there was already a copy of this view in the data structure with a different expression or different mask, right? Legion will unify those and do the right thing. So there's insert and validate all, right? We kind of saw some of these methods over here being used over here in this particular function here, right? We've got the test for dominance, we've got invalidate down here, insert over here, invalidate all, but right. So these methods all get called over here in this in the equivalent set object over here. Right, and here's testing for dominance and stuff like that. So you can see these methods are all implemented on this class. I'm not going to go show you these. They're kind of hairy index-based expression field mask stuff, but the logic is pretty straightforward. It does exactly what it says it does, and deals with all the corner cases and stuff for you. So effectively, as you're running along, capturing a trace, right? The equivalent sets that you're touching as part of your physical analysis are tracking this frontier of these trace view sets, and keeping track of the frontier of preconditions, postconditions, and anticonditions. Are there any questions about that so far before I move on to the next step? Okay, seems like that is pretty straightforward. Okay, so let me actually go on to the next step, which is talking about, when you get to the end of a trace, right, how do you actually record all these different preconditions, postconditions, anticonditions, and so forth. So if let's see, let me see if I can find, there's the capture method. I want to look at how we actually capture these I've forgotten the name of the place over here. We go. Okay, here's the name of the method that I'm looking for. Okay, so at the end of a trace replay, end of a trace capture, the thing that we want to do is check to see whether this template is something that we can record to be a future trace for being replayable, or whether it's a template that we can't, right? And Legion has a little bit of a restriction today that says that a physical template, which is a copy of a physical trace, right, for a particular set of mapping decisions, right, we currently only make them replayable if they're what we call item potent, and we'll talk about what that means, but it simply means that effectively you can replay the trace back to back many times without having any testing for preconditions and postconditions and stuff like that, and we only allow for item potent replays. So we want to check to see if the trace actually has this property. In fact, let me just show you where this, you can see this check replayable method is called here at the end of the physical template finalize, which effectively gets called by one of the trace capture operations at the end of the trace capture. So it's going to check to see whether this is a replayable template. And in order to do that, it needs to go fetch all the information out of the equivalent sets, associated with that we touched during the capturing of this trace. So we can go look at check replayable. There's a sharded version of it for doing sharded templates, but we'll skip that today and just focus on normal tracing cases for single node kind of executions without control application. Right. So the first thing that we're going to do, right, and you can see there's actually some good descriptions here of what actually happens, right? But as we've been capturing this trace, we've actually tracked the names of all of the logical regions that we've done physical analyses for as part of operations inside of this trace, right? And that's in this trace parent rec indexes. And I think if I actually let me show you where this is in the header file over here. I thought it was over here. I thought trace parent rec indexes was over there. Maybe I'm not typing right. Oh, here it is. I don't know why am I. Oh, trace region parent rec indexes. That's what I wanted. So effectively, this is a data structure on a physical template. So we're in the physical template class. I think up here, if I scroll up, make sure we're in the right place. Yes, this is the physical template class. So back down to where we were. Right. So this is a data structure that effectively tracks the names of all the logical regions that are actually recorded, for operations inside of this trace. And actually, there's actually two data structures here that we record, just so you got it all up to date. We're recording the sets of regions with the fields that we've analyzed as part of operations inside of this trace as we've been capturing it, right? And we've also recorded effectively the mapping from those regions to the parent region requirement that's associated with them for privilege purposes. And you'll see a little bit why we need that later. But effectively, these two data structures are what tells us, which regions we need to consult as part of, as part of doing this capture operation at the end of the trace. And so any operation that touched a logical region for a set of fields will get recorded inside of this trace regions data structure. Okay, so if we come back over here, and we can actually see we're going to iterate over this trace regions data structure here. And the first thing we're going to do is we're actually going to get the names of all the equivalent sets that are associated with those logical regions, right? That we may have touched as part of our analysis, right? And so what we do is we're actually going to do this versioning analysis, which effectively will fill in, the set of version info objects, which are, just wrappers around a set of equivalent sets and the fields that you're tracking for each of those equivalent sets, right? Just as if we were doing like a normal physical analysis for a normal operation, whether it's a region requirement, a task, or a copy, or anything like that. They do this same perform versioning analysis call, right, to get the names of the equivalent sets associated with the particular region and set of fields, right? And so we do this analysis the same as we would for any other operation, but effectively, we're doing it now for all of the regions that we've recorded, as part of this particular trace capture. And in particular, let's see, trying to remember what this part is. Oh yeah, we just have to wait for all those things to be ready, right? And let's see, we're filling in some data structures that we're going to need here down at the bottom, and I'm trying to remember exactly what we need. But oh yeah, we're creating a mapping here between each of the equivalent sets and the parent region requirement that produced them. So this is sort of like some bookkeeping code. It's not terribly important. The most important thing is that we're getting these set of equivalent sets, associated with each of the regions that we need to actually analyze. And we're filling in this current sets data structure. Effectively, the set of equivalent sets and the set of fields on each of those equivalent sets that should have data associated with the capture of this trace that we're going to need to go grab. And we've got this other data structure here, which is effectively mapping these equivalent sets to the parent region requirement, where the privileges were derived from. That's sort of useful for doing some of the like perform versioning analysis calls and stuff, but it's mostly bookkeeping. The really important data structure is this one, the current sets data structure. Okay, so as we exit this block of code here, we've now got this current this set of current equivalent sets that we need to go analyze. And what you see is we're going to iterate over each of these current sets, and we're going to get trace condition. We're going to create a trace condition set object for each of these equivalent sets, and each one of these trace condition set objects is going to grab the state of the trace capture, or it's going to capture the state of the tracing for each of these equivalent sets at the end of at this point in the execution, right? Let's see, and so we can actually go and do that. Do that process. You'll notice there's a little catch here that looks a little bit redundant, and you can actually see I have a comment here about it. Effectively, it looks like it's recomputing the equivalent sets associated with this trace condition set, but really that's just doing a registration because effectively this trace condition set is going to be the thing that we use for testing the preconditions and postconditions, anti-conditions going forward inside the trace, and it needs to know the names of the equivalent sets that it's tracking, even for future replays, right? And of course, the set of equivalent sets that are representing a logical region could change over the course of the program, right? You might replay a trace and then start running some non-traced code, which then does some refinements, which change the equivalent sets, right? And this trace condition set needs to be notified of all those refinements and stuff that occur down the stream. So if you ever go to replay this trace in the future, Right, it knows how to do that. So this recompute equivalent set thing here is a little redundant. We actually already know that there's exactly one equivalent set that's associated with this trace condition set at the point of capture. But further down in the execution of the program, when we go to do replays, it might change. And so this is effectively just recording this trace condition set, or getting this trace condition set to start tracking the sets of valid equivalent sets, associated with a particular logical region. And so that's why we do this thing, or do this sort of additional recompute equivalent sets call here. It's slightly redundant, but the cost is pretty minimal compared to, and it's sort of a one-time thing. Just when you go to do the capture, it's and then for all the rest of the time, for all the replays of this trace, we'll be able to actually benefit from that registration. And the most important call here is this one, right? Effectively, we're going to say to this trace condition set, go capture all of the state in this equivalent set, right? It.first is the equivalent set. It.second is the set of fields for that equivalent set. Go capture all of the tracing state from that particular equivalent set. And we can actually go look at this call over here in equivalent set. I think there's actually an extra level of indirection here. Let me just show you, pop open a new window here because I don't want to lose my place over here. If we look at trace conditions set capture, right, you can see it just goes and does the capture on the equivalent set, records some additional stuff, right? There's just a little level of indirection, but it calls this capture trace capture trace conditions function call, which over here is right here, right? And so you can see this call, like effectively, if you're not the logical owner, it'll forward the request on to whatever node is actually the owner node for this logical equivalent set, wherever it is in the machine, right? And go grab the state and bring it back, right? Recording a ready event for when that's actually done. But in the case where we're actually on that node where we want to be, right? We can effectively just grab trace view sets for each of these tracing preconditions, right? And you see we actually extract the overlapping parts, right? Because an equivalent set might actually span like multiple logical regions, right? And so we only want to pull out the part that's actually relevant to us, right? So we actually find the overlapping parts, right, and then merge them over into these trace view set objects, and then we can send those results back to the trace condition set to capture them, right? And so you call this, here's the distributed case where you actually have to send a message. So you pack them all up and ship them over to the node that's looking for them, right? But in the common case, you're already on that node, right? And so you just call this receive capture method, right? And then you can go through at the end and invalidate all the things that you overlapped with, because now you don't need to record them anymore, right? This equivalent set is done recording for this particular trace, right? If we look at receive capture back here, over here on the trace condition set, you can see that what it does is it effectively grabs these precondition, anti-condition, post-condition views. It takes ownership of them, right? And then it does this transpose operation. And let me show you what this is, because this is actually an important sort of like transpose the representation of the data that actually is important for how we're actually going to analyze the equivalent sets. So let me actually talk through what that does. First, we need to look at this trace view set. Right, so we actually looked at this beforehand because this is the same as the one that's in the equivalent set. And you'll notice that it stores this data structure as view expers, right? So the logical views are the keys, right? And then inside you've got values, which are field or index-based expressions for sets of fields and stuff like that. But if you look at like this trace condition set, it actually wants the data in a slightly different representation. It actually wants it in this. In an alternative view, which is like, for each index-based expression, it wants the sets of views, associated with that index-based expression in fields, right? And so what this transpose uniquely call is doing is effectively changing the representation of the data from tracking, for each view, all of the index-based expressions and fields that it's valid for, to one which is for each of the index-based expressions, all the views and fields, right? And so that's what this transpose uniquely is gonna do, and that's actually useful for doing the trace capture or for testing preconditions, right? And so the trace condition set wants their data represented in a slightly different way than how we capture it, than how we do the recording, right? So testing preconditions and postconditions, is slightly different than how we capture it. So this transpose uniquely is just a different representation of the same data, just recorded inside of our trace condition set here instead of in these precondition, postcondition, anticondition views. There's some index basic or some reference counting code here to help make sure we're tracking references on all the views and index-based expressions correctly, but that's all for garbage collection. Nothing terribly interesting there from a functionality standpoint. The transpose uniquely part is the important part of the capture. Okay, let me pop the stack and come back up here. Right, we looked at this. So effectively, the thing to remember is that at the point where you've finished this loop right here, what we've got now are for each equivalent set, in our current trace, we've got a trace condition set that has gone and captured the metadata associated with this trace capture to for a particular logical region. We've sucked out all the tracing state into one of these trace condition sets for that logical region. And we're going to be able to use this information now to test, first whether the trace is replayable, but then also we can actually use it, in the case that is replayable, this will also be the objects that we use for testing whether preconditions have been satisfied when we go to actually replay the trace. Let's see, any questions about that before I move on to looking at, what we do with these trace condition set objects? Okay, no questions about that. All right, so we do all this work, right? One thing you'll notice is that there's actually events associated with tracking when we've done all of this capturing and stuff. And we actually do have to block and wait for that to happen, right? We can't really go on before we've done all this capturing and gotten all of our trace condition sets. I suppose technically we could build a continuation here if we really wanted to make this, technically fully non-blocking in Legion and defer everything. This happens so infrequently, and it's like effectively I'm willing to pay some cost for trace capture as long as trace replays are very efficient, right? And so we actually just block in line here, waiting for all this to be done, rather than building a continuation and having to do one of those things. But I guess actually, so actually should say, because it's going to show up right here in this block of code, there is one really interesting thing that actually happens here with control application that I should point out, which is that let's see, it's possible for multiple shards to have recorded that they have operations that touch the same logical regions or touch logical regions that are aliased with each other that need tracing data from the same equivalent set and so forth. And so one really kind of strange but actually kind of working case is that, let's say you actually had multiple shard templates, right? So imagine you've got a control-applicated context with 2 shards, right? And they've each recorded that they had some task in their shard that they mapped that touched the same logical region, right? Both of those sharded templates, right? There's going to be a template on each of the shards. They're each going to try to record or try to do this capture on the same equivalent set, right? And one thing we don't, this is kind of a benign race, but what we do is we don't try to specify exactly which of the shards should actually do the capturing of this trace condition set for that particular equivalent set for the logical region. We just let whichever one gets there win the race and grab the data. You actually notice over here in, let's see, where is Legion analysis? You'll notice that this capture trace conditions is protected by a lock, right? And it's an exclusive lock. So, whichever shard ends up getting to this equivalent set first to grab the capturing will actually win the race. And it's not an error for the other ones to get there too and try to do their recording, right? Because effectively all we need is that one shard records, the preconditions, postconditions, anticonditions for a particular equivalent set. They don't all need to test it. Just one of them will need to test it, and then all the shards will test their conditions and see if they all agree that they've all been satisfied. So whichever one happens to get there first will win the race and grab the metadata, and whichever one gets there, second, just will find an empty equivalent set without, any tracing data there, and we just allow that to be, to kind of work. And that's going to explain this case right here. So what we're going to do is we're going to iterate over each of these trace conditions, right? And we're going to check them for is replayable. But the first thing that we do before that, right, is we test for empty, right? And this block of code here is literally because of control application, right? Effectively, it's here because multiple traces or multiple shards, right, could have each tried to capture the same trace condition set for the same logical region, or for partially overlapping ones. and they just end up finding, that some other shard had gotten there first and grabbed the tracing data, and that's totally cool, right? And so we just like ignore any trace conditions that are actually empty, and we actually remove them from the set. We don't actually care about them anymore because some other shard is actually already handling them for us. So that's how you can hit this this is empty case, which is kind of interesting. But effectively what happens next is that if it's not empty, right? If we actually grab some metadata for this particular trace condition set, we're going to test this this replayable condition, test to see whether the trace condition set actually is able to be replayed, right? And we're going to test this for all the trace condition sets, and they're all going to have to be replayable in order for this whole trace to be replayable. Right, so let's actually go take a look at that is replayable method. I'm going to keep our position over here. Let's actually take a look at is replayable. Oh, here we go. Okay, so we're going to test is replayable, right? And there's actually two things that have to be true in order for this this trace condition set to be replayable, right? And that is, the first condition that we're going to test is that our precondition views are subsumed by our postcondition views. And what that means is that all of the preconditions for this trace, like all of the data that we're going to read, as all the instances that are going to be read for this trace, they have to also be written by this trace with one exception, right? And that is effectively, that you have to either, and the reason for that is like effectively, if you're going to replay the trace back to back, you want to ensure that all the valid instances, right, that you're going to be reading inside the trace are also written by the trace. That way, when you replay a trace back to back, you know that the instances are still valid even after a replay, right? And so effectively, this subsumed by call will actually do this test to make sure that for each view in the postconditions, for each view in the precondition, we will find a corresponding view in the postconditions, right? And there's one exception to this, right, which is effectively you can have views in the preconditions which correspond with logical regens, which are not written by any of the views in the postcondition, right? So if we actually go look at subsumed by, let's actually see if let's take a look at that. We can look at this this particular test. Right, so effectively we're, I should have popped this open in a new window because I want to flip back and forth. Let's see if I can do that quickly here. We were in check replayable. Oop. Not that one, not that one. What is it called? Is replayable, sorry. Right, so effectively we're testing one of these trace view sets against another, right? Testing the precondition views are subsumed by the postcondition views, so we come over here. Oh, I should have stayed in that window. Subsumed by. So our this member is the preconditions, right? And the thing that we're testing against are the postconditions over here, right? And so effectively, what we're doing is we're testing for each of our views in each of our instances that are in the precondition set. We want to either find a corresponding view in the postcondition set, or we want to allow this independent case, right? That's effectively the case where you actually have like a physical instance that's read by a trace, but it's never written by, or no other operation in the trace wrote to another instance, which is a copy of, the same or overlapping logical region inside of the trace, right? And so effectively, you're either testing that you can find it, right? In this allow independent case, you test to see if you can find it first. If you don't find it, then you go through and check to make sure that you've removed all the independent, or see if it's independent from all the other things in the postcondition. And if it is, then you're good, right? Effectively, that's this continue branch down here, right? Effectively, you found that you couldn't find the operation itself, but you found that, or you couldn't find the instance itself, but you found that there were no other instances that also scribbled to a corresponding overlapping set of expressions and fields, and therefore it's good to go. Right, and of course, like if you're not allowing independent, which happens in one other case, but not in this particular case, if you notice, like here we're actually allowing true for allowing this independent test over here. That means that effectively you don't allow the read only case, but Yeah, we do allow this independent case for testing this this particular some subsumption case for replayable here. Okay. So we test that subsumption condition right first and see if all of your preconditions are subsumed by your postconditions. And if not, right, then we mark that you're not replayable and you're not subsumed and all those things, right? But if you're still replayable, we also do this other test here, right, which is testing that the postcondition views are independent of the anticondition views, right? And effectively, this says that these anticondition views are pretty much exclusively reduction instances, right? Of saying these are things that these are instances that should not be that are initialized as part of the trace and therefore cannot be valid instances coming into the trace when we go to replay it, right? Because we're going to overwrite data inside of them by doing a fill, to initialize the reduction instances and stuff inside of this trace execution. So doing a fill to them would actually overwrite data inside of the reduction instances, right? So we want to test that reduction views are not valid at the end of the trace, right? They need to be independent of the anticondition views, because otherwise you'd be effectively losing data if you replayed this trace in a back-to-back way, right? And so we test that condition as well, right? And this independent of works exactly as you might expect. It's effectively checking that effectively there's no overlaps between any of the views and expressions and fields and stuff like that, right? And so there's a bunch of cases in here, but really it's just doing an independence test of all the views and instances and so forth. Okay.
Mike, could you explain the independence between postconditions and anticonditions again?
Okay. Right. So imagine that you had a trace where you capture a trace, right, and effectively you use a reduction buffer and you for the first time inside of the trace, right. But then you don't apply the reduction as part of the execution of the trace, right? So effectively, the reduction is going to be consumed after the trace is done, right? So the reduction is still valid at the end of the trace, right? So in that case, the reduction instance would appear in both of the anti-condition views and the post-condition views, right? So in the anti-condition views, because you used it for the first time inside of the trace, right? And it's still valid at the end of the trace as part of the post-conditions, right? So if you replayed it back to back, right, the trace back to back, what you would actually end up doing, right, is overwriting the reduction instance on the on the first replay or the first redundant replay, right? You'd actually end up doing a fill and overwriting reduction instance data that had been recorded from the prior replay, right? And that's not allowed, right? Because effectively that would be losing reduction data. Does that make sense?
Yeah, I think that makes sense.
Right. So effectively, this is testing to make sure that you're not stomping on top of reduction instance data, right? That you've produced in one part of the trace. In one replay of the trace, the next replay is not going to stomp on top of that reduction data. Yeah.
But if early in the trace somebody then read the reduction data, we could I guess it wouldn't show up in it
wouldn't be in the postconditions.
Anti-condition views if that was actually the case.
It would still show up in the anti-condition views. It would not show up in the postcondition views because it had been consumed. Right, consumption of a reduction instance will remove it from the postcondition views. Right, so if your trace consumes the reduction instance before the trace is over, right, then that instance will no longer show up in the postcondition views.
But if your trace also but if your trace reads some reduction data, say before you reduce to it, then it also shouldn't be an anti-condition.
That's right. Yeah, effectively, if you read the reduction instance for the first time, then it shouldn't be. If it was a precondition, then it shouldn't be. If reduction instance shows up in the precondition, then it shouldn't be in the anti-conditions because it was priorly consumed inside of the trace, and therefore it's safe to to initialize it inside of the trace. Right.
Yeah.
Yes.
Makes sense.
Yes. Okay. And there's a little optimization here, just cleaning up some memory, right? Effectively, once we're done with this test, we can actually get rid of these views and keep around, if I pop back over here, we had both these are the data structures that we grabbed as part of the trace capture, right? And these are the data structures that we keep for actually, as part of the trace, replay and stuff. This is the things we transposed over to these things. right? And effectively, once you're done testing this is replayable thing, you can actually get rid of these data structures that you grabbed as part of the capture, these precondition, anticondition, and postcondition views. You don't need them anymore after this for testing replays and stuff like that. So effectively,
but
that's
if we switch to non-idempotent traces, we couldn't just early delete them, right? Because we'd actually need to issue the tests.
No, I think you can still get rid of them, because the data structures we're going to use to do the tests are they're going to be these data structures, and I'll hopefully show that before the end of this. These are the things we're actually going to use to test the preconditions and postconditions and or effectively preconditions and anticonditions are what we're going to use to test for whether it's safe to replay the trace, and postconditions are what we apply after we're done replaying the trace if we're not going to do an idempotent, back-to-back trace replay. Right, and so effectively, after you're done testing is replayable, these data structures can always go away, right? In fact, like if we were supporting non-idempotent traces, right, then effectively what's going to happen is this is replayable call here will just it'll become a performance optimization instead of like a failure to capture kind of thing. So, but yeah, we'll always be able to clean these up right here. Okay. And so popping the stack to finish out the trace capture stuff, right? We do this is replayable test on all of the trace condition sets, right? And we check to see if any of them are not replayable. We try to report why they were not replayable, so we can at least give the user some hints as to like why we weren't able to capture a replayable trace, right? And we can break out, but if we make it all the way to the end, then we've captured a replayable trace, and it's going to be able to be used for replaying, which is a good thing. Right, and so that's effectively how we do the trace capture. Are there any questions before I move on to like testing the preconditions, then applying postconditions using these trace condition set objects? Okay, no questions. So let's see here. So the important methods, I can dismiss all of our meeting invites. Let's see here. Let's see. I'm looking for. Yes. Okay. So I'll share these two methods, and I'm not going to show you where these are called from, but effectively these are called from trace. These methods will be called by trace begin or like trace begin and trace complete operations, right? Effectively, when you go to replay a trace or a template. Right, you want to. The first thing that I said is you want to test whether all of these preconditions have been met, and then if you're at the end of a trace replay and you're not going to be doing another back-to-back trace replay, you need to apply the postconditions. These two methods here are the things that do that. Check preconditions and apply postconditions. Right, they do exactly what they say. Right, so effectively, this is the method that gets called on a template whenever you want to check to see if it's safe to replay this particular template. Right, and then if you're done doing replays and you're going back to normal execution, right, you need to apply the postconditions from this template back into the equivalent sets, right, to actually tell them to go and update the state with all the postconditions of this particular trace. Right, so for checking preconditions, we're going to iterate over each of our trace condition sets, right, inside of our physical template. And we'll call this this test require method, which will actually test the preconditions on that trace condition set, right? And then we're going to wait for the result and be able to check the results on each of the trace condition sets, whether they were satisfied or not. Similarly, if we apply post conditions, we're just going to iterate over all those and call ensure, and that will actually go and apply. I should really call this apply, but effectively go and apply the post conditions out to each of the equivalent sets. So let's actually take a look at test require. And ensure, or we'll look at test require, check require, and then ensure to see what's actually going on in there. So first, let's do test require. So, this is effectively the first thing that we're going to do on our trace condition sets. You'll remember that I told you before that these trace condition sets are something that track the set of equivalent sets associated with a particular logical region. One thing that may have happened, like in the middle of running non-trace code, right? You're out running along, doing normal tasks and stuff without doing trace replays, right? You could actually come into this trace condition set, and there might have been some refinements that actually change the sets of equivalent sets for particular logical regions. And this trace condition set, I'm not going to get into this a whole lot today, but it is a special. I'll at least give you a pointer here to the right thing. and then you can go look at this maybe offline, or maybe it's a topic for a future lecture. But it's an instance of this base class called an EQ set tracker, and that's an equivalence set tracker. And what that is effectively it's a data structure that that actually tracks the current sets of equivalent sets for a particular logical region inside of the program, right? And anytime the set of equivalent sets gets refined or changed for a particular logical region, these EQ set trackers will get notified that effectively their data is stale. They don't actually get told what the new equivalent sets are yet. They just get told that that like their equivalent set, their names of the equivalent sets that they were tracking for this particular logical region are now stale, and they need to go update them. And so that's what this invalid mass is tracking. Effectively, it's the name of all the equivalent sets that we actually need to go update, right? Effectively, they've been refined or changed in some way since the last time we either captured this trace condition set, or since since we've last replayed the trace or something like that. And so we need to go update our set of equivalent sets. We call this recompute equivalent sets method to go get it. Of course, if nothing changed, right, we get to skip this block, right? None of the equivalent sets actually changed, and we can just go on to our next step. But effectively, that's what's happening in this little block of code here, is that if their equivalent sets got refined since we did the capture, right, or the last replay, we'll actually go recompute and update our set of equivalent sets, right? But once we've got those set of equivalent sets, it's really easy. We make for our preconditions, we make an invalid inst analysis. And this is an example of let me find the right file here, invalid inst analysis. You can see this is a kind of physical analysis, similar to like other kinds of physical analyses we've looked at, like update set and stuff like that. And what it's going to do is it's going to go iterate over all the equivalent sets and test to see if it can find any equivalents or any of our instances which are not valid, right? So effectively, it's going to iterate over for each of the for all the expressions and all the views and fields for each of those expressions, right? Look over all of the equivalent sets, and then go try and check to see if you can find any instances which are not valid for that particular expression, right? And if so, right, that's going to be a violation of the precondition and not allow the trace to be replayed, right? But of course, if we can't find anything, right, ideally we're going to have an empty set, right? Effectively, each of these invalid inst analyses are not going to be able to find any instances which are not valid. Then we'll be able to replay the trace, right? And so effectively, this invalid inst analysis, this is a bunch of stuff, but this is effectively the equivalent set traversal code, right? It's calling analyze on each of the equivalent sets, and then if you've got any deferral methods or doing remote traversals, right, on those equivalent sets, it goes off and does those things. But this is a pretty standard physical analysis in terms of iterating over the equivalent sets and testing some condition, right? And similarly for the anti-conditions, we do something different or something similar, right? Like effectively, we're gonna create one of these anti-valid inst analysis, which is like checking to see whether we can find an instance which is valid, right? When we hope that it's not actually a valid copy, right? Like, and this is again for the reduction instances, we want to make sure that they don't have valid data, right? As part before we replay this trace, because we're going to fill them and stuff like that. And so we iterate over all of our anti-conditions and make an anti-valid inst analysis, which is also a kind of physical analysis. So there's an anti-valid inst analysis here, which is also kind of physical analysis, right? So it traverses over all the equivalent sets and checks our postcondition for us, or sorry, our precondition for us, right? And we just record all the events for when all these analyses are done, right? We stick all those in these applied events, right? And eventually, as you saw, once we've done that for all the trace condition sets and all the analyses have gone off and done all their tests, we did that. We did this, effectively we kick them all off, right? And then we just wait, right? Make sure that they're all done, right? So that way they're all running in parallel. All the trace condition sets have all their analyses, all scrambling around, testing equivalent sets in parallel, doing a bunch of work, right? We wait for them all to be done, right? And then we can actually test whether any of them found anything that they shouldn't have, right? And so test require is actually, let's see, where did it go? Where did test require go? There we go. Oh, sorry, I wanted to check require. There you go. Right, and so this is a really simple test to effectively see, like, for each of our analyses, did you find anything that was invalid? If so, like, our trace preconditions are not satisfied, right, so it's a false. Similarly, for our anti-condition analyses, do the same test, right, and then we can return the result, right. It's a pretty simple, thing to just send off those physical analyses to go do the tests, right, and then capture them when they're done, or capture the result, of all those analyses to see whether the traces can be safely replayed or not, right. And similarly for ensure, right, ensure is very much a comparable thing just happening when we go to say this trace is done. We replayed the trace, but we're not going to be doing any back-to-back trace replays after this. So we need to record, the changes to the physical or to each of the equivalent sets associated with this trace. Effectively apply all the post conditions, right? And so in this case, again, we've got this block of code here checking for, have the set of equivalent sets changed since the last time we were here, and if so, we recompute them. Otherwise, we go off and for each of our post conditions, we make an override analysis. An override analysis is, again, another one of those physical analyses. This one will actually go and mutate each of the equivalent sets to effectively overwrite the state for particular expressions and fields and stuff, and scribble in the names of the current valid instances and remove any it'll effectively remove the currently valid instances in the equivalent set and then overwrite them with the new values, the new instances, the valid copies of data. And so we make an override analysis for each of our expressions, right? And traverse it for each of the equivalent sets and kick it off, right? And that will actually go and scribble on top of the analysis, or on top of the equivalent sets, and update them with the latest post conditions as of the end of this particular trace. So that's how the trace condition sets go and update that. Okay. Any questions about that? I think this covers the bulk of like what these trace condition sets do for the templates, right? And how you actually test preconditions and postconditions, both capturing them as well as testing them and replaying them for trace replays. So any questions I can answer because we're almost out of time.
Yeah. So very quickly, then how do we like when you're actually doing you happen to be replaying two traces back to back that are idempotent, where do the precondition check gets skipped?
Yeah, so that actually happens above in the operations. So let's see if I can remember off the top of my head where that is. This code is some of the nastiest code in the tracing, and I'm as I've said before, I don't like the fact that this happens in logical analysis because it monkeys where it should happen. Let's see. Let me try and remember exactly where to go for this. It's not the begin up. Let's try trace replay up. Let's see here. So this is the path where we're actually testing preconditions here. But I think, it's weird because we're looking for a negative. We're looking for a case of the path where we don't call test require and stuff, or test preconditions. What was it called? Test require was called in check preconditions. Let's try and do this backwards. Right, check template preconditions. Right, so this is the call on the physical trace that actually, is looking for a template that can be replayed. Okay. Right, so, right, I was looking in the right place. Right, so, okay, so effectively in a trace replay out, which means we've already captured this trace before, right? Right, we actually skipped this branch because, so effectively, if you were doing a back-to-back replay, physical trace get current template would be non-null because, effectively, physical, and this is the weird thing, is that this physical trace actually remembers the name of the current template, which is the one that was replayed before, right? And so effectively, it would be tracking the state. Effectively, it remembers that the most recent thing that it did was to replay this current template in the previous iteration, and there was no intervening code that caused it to be, for the current template to be invalidated, right? Like if there was a non-trace code in between the prior replay and this replay that we're about to start with this trace replay op, right? Like effectively, then if either of those two things had occurred, right, then current template would be null, and we come down this path. But if current template is not null, that means that we already had a prior replay that we did before, right? You can actually see that condition here, right? Like this is, well, actually, this is a little misleading because replaying could be for the first time or it could be recurrent. But effectively, the way that you skip the testing of the preconditions are, your current template would be non-null, so you would skip this whole if block, right? But inside of this if block, this is where we would actually do the testing of preconditions, right? This call right here to check template preconditions would actually go look at each of the templates and see if you could find one that has its preconditions satisfied. And if so, it'll actually set the current template, right, to be that new template that we actually found. Does that make sense?
Yep.
Okay. So we would skip that in the case the current template is non-null, right? Yeah, and that's how you would get past the testing of the preconditions on the replay. Like I said, I am not a big fan of this code. I did not write this code, and I plan to clean it up in the future, but it is what it is at the moment.
All right. I also have like a more long or a more specific question about the equivalence set update, like the method that is
Sure.
updating the trace conditions.
Okay.
It's kind of what I was asking about. If you could jump back to that piece of code.
The test require.
No. It was like update trace valid views, I think.
Update trace valid. Oh, and okay. Let's yeah.
Depending on how much time you have to argue. Yeah, update tracing valid views.
That's not the right one. It's this one.
This one, yeah. Okay, so if we see that we're reading, well, actually, so what does it mean for has read to then say view is reduction kind, or?
So
I guess yeah.
Yeah, you can be reading, right? Right. I guess like just to be clear, let's expand the macro.
I guess you're doing a read on a logical region, but the instance you're reading is a reduction buffer.
No, technically,
no.
I mean, yeah. So this is the expansion of that particular macro there, right?
Okay.
Right. So effectively, it's saying reductions are a kind of read for the purposes of traces, which is a little strange, but that's the way it is. So reduction privileges, where'd it go? Reduction privileges will come down through this path, right? Because technically, reduction is eventually going to be read, right? It is a kind of read because you might be like replying or applying on top of an existing reduction instance, right? You might have multiple reductions that are reducing to the same reduction instance, and so it technically is a kind of read, even though the user can't actually see the results, right? Which is why it comes down this path.
Okay. So the I think this is what I was asking earlier, where so as soon as we see a reduction, we like add it to the anti-conditions, right? Or then, but it seems like we also need like a read frontier where we see like I have read something that was then reduced. So if I read like a pending reduction, then I can remove it from the tracing anti-conditions or something like that.
It could be missing, yes. that particular case could be missing in here, yes.
Okay.
But you probably only want to track it on reductions and not on other things, because it kind of already gets handled for normal instances. But yes.
Okay. I'll look at that.
Yeah.
All right, thank you.
Yeah. So, yep. It's certainly possible that we haven't handled all the reduction cases in here quite correctly. Again, I'm not a big fan of this code, but it is what it is.
Wait, sorry. Also the hold on. Oh yeah. So then the view. Wait, can you scroll down again?
How far?
The has right. Okay. Never mind.
Right. These are just the postconditions. This should be pretty non-controversial, I think.
Yeah.
Right. If you're either writing or reducing, then you stick it in the postconditions. It's pretty obvious. And I think like invalidate should only be true if you're actually writing. I think if you're reducing, invalidates will go to false. I believe that should be the case. This invalidates parameter here should be false for reductions.
Okay. All right. That's all my questions for now. Thanks.
Okay. Anybody else? We're 2 minutes over time.
It's just I'm all that's left.
Okay. All right. Well, great. I'll talk to everybody next week.